Welcome back to Advanced Calculus. Today we are in Lesson 9. What rules should open set follow? Last time we discovered something slightly uncomfortable. A sigma algebra is powerful, but it does not know what close means. It can tell us what is measurable, but it cannot tell us why 1 over n gets closer and closer to 0. So today we are going to build the missing structure. That structure is called a topological space. And the main question is simple. If open sets are supposed to describe closeness, what rules should they follow? Last time, Lesson 8 asked why sigma algebra are not enough. A sigma algebra tells us what can be observed. It is like a rule book for information. It says this set is measurable. This set is a load. This set belongs to our observable world. But here is the problem. Observation is not the same thing as geometry. Knowing that a set is measurable does not tell us whether two points are close. So we need another structure. Not a replacement for sigma algebra, but a partner. Here is the difference. The statement A is collection. It is measurable information. It says the set A belongs to our sigma algebra. So this is about what we can observe or measure. But the statement x sub n to x sub xn approach x is a completely different kind of statement. This is not just information, this is geometry. It says the sequence is approaching a point. A sigma algebra can handle the first statement, but it cannot speak the second language. It cannot look at the sequence and say, yes, you are getting closer. That is why we need topology. To talk about limits, we need a language for three ideas. First, near. What does it mean for one point to be near another? Second, neighborhood. What kind of regions surround a point? Third, eventually inside. When we say x sub n approach x, we mean that after some point, the sequence stays inside every small region around x. So convergence is not just about points. It is about points interacting with neighborhoods. And this is the beginning of topology. Topology is a language of nearness without necessarily measuring exact distance. Now we introduce the central object, open sets. An open set is a region where points have room to move. Think of standing inside a room. If you are truly inside a room, you can move a little left, a little right, and still stay inside. But if you are exactly on the wall, then one tiny step may take you outside. That is the intuition behind open set. If x in U, then there is still space around x. The point is not trapped on the boundary. So open sets are the first formal way to talk about local room. Lesson 8 ends with this question. What rules should open set follow? This is a very important moment because we are not just memorizing a definition. We are asking, if open sets are supposed to describe a region of nearness, what behavior should they have? The answer is they should satisfy three rules, and those three rules are exactly what we call a topology. So topology is not magic. It is just a rule system for open sets. Rule 1 says the empty is in topology and the x is in topology. The empty is open. The whole space is open. At first, this might feel strange. Why is the empty set open? Because it causes not contradiction. There is no point inside, so there is no point that violates the idea of having room around it. It is like saying everyone in the empty classroom is doing homework. Technically true, because there is no one there to fail the condition. And X is open because it is a whole universe. If you are inside the entire space, there is nowhere outside the space to accidentally step. So every topology begins with empty and X. Rule 2 says the infinite interaction of open sets are open. What does this mean intuitively? If each U sub k is a safe region, they satisfy finite many satisfied conditions at once should still give us a safe region. For example, maybe one open set says you are close enough to this point. Another open set says you are also inside this region. If there are only finitely many such requirements, we can still keep a little room. So, finite overlap preserve openness. But the word finite is very important, and the next slide explains why. Why only finite intersection? Because infinite intersection can collapse. Look at this example. Each interval is open. Each one gives some room around 0, but as n gets larger, the interval gets smaller and smaller. Eventually, after intersecting all of them, the only point that survives is 0. So we start with open interval, but the infinite intersection becomes 0 set, and 0 set is not open in real numbers. Why? Because if you stand at 0, any tiny movement takes you outside 0 set. There is no room to move. So arbitrary intersecting of open sets do not have to be open. This is why topology only requires finite intersection. Rule 3 says arbitrary union of open sets are open. Here the intersect can be arbitrary. It does not need to finite. It does not even need to be countable. Why is union safer than intersection? Because union means we are gluing open region together. If a point lies in the union, then it lies in at least one open set. And inside that open set, it already has room to move. So the union still behaves like an open region. Intersection makes requirements stricter. Union makes region larger. That is why arbitrary unions are allowed. Now we can finally define the object. A collection is a topology if it satisfies these 3 rules. It controls empty and X. It closes under finite intersection. It closes under arbitrary union. Then this pair is called a topological space. This means the set X is not just a naked set anymore. It now carries a structure. That structure tells us which subset count as open. So the key sentence is topology is the structure of openness, not distance, not measure openness. Now let us connect this back to the big picture. We start with open set. Open set give us topology. Topology let us talk about continuity and convergence, and then in measure theory, open sets generate the Borel schema algebra. So the bridge is open set topology, continuum and convergence, and Borel sigma algebra. This is why topology appears in a measure theory course. It is not random. Measure theory needs topology because Borel sets come from open sets. So geometry enters measure theory through topology. Next time we will ask, where do open sets come from? One concrete answer is metric space. A metric space gives us a distance function. Distance gives us open ball. Open ball gives us open sets. And open sets give us a topology. So next time we move from closeness to closeness. Topology says what regions are open. Metric space says how far apart are the points. And once we understand both, Borel sigma algebras will feel much more natural.